Howdy, my name is Isabella Oaks.
Howdy, my name is Shri, Gaddad, and
We've been a part of AJ's Deep Group this past semester, and we've been working on a quantum cryptography demonstration. Quantum cryptography utilizes the uses of quantum mechanics to encrypt and decrypt messages without a way to break the code. Essentially, you have a sender and you have a receiver, Alice and Bob respectively. Alice sends Bob a message, and that message is unable to be decrypted without having a key.
so what we have here, what we've been working on for this past 2 semesters has been a classically based analogous version of the BB84 quantum key distribution algorithm. And the only difference between this and a true quantum setup would be that we would have a single photon emitter versus a regular laser that we have, and we'd have the appropriate detectors instead of light-dependent resistors. But the main concept is basically the same. We're using photon polarization in order to securely generate a key that both the sender and receiver can possess that will be used to both encrypt and decrypt the message at the same time. And the fascinating part about this algorithm is that we also have a way of detecting interceptions, and so the receiver and sender can both know that they're communicating on a not secure channel.
So for the actual demonstration itself, we have a laser module connected to the Arduino circuit. We have the filter, half-wave plate, and these are 2 polarizers. We have the beam splitter, which goes in either direction depending on the polarization of this. And then we have 2 light-dependent resistors connected to the detection circuit.
All right, so the idea behind this is we have the emitter here. The laser will send light through here. This will filter it and clean up the laser and come to this half-wave plate. What this will do is essentially determine the angle of polarization. And so there are different ways to go about this. I could set it at a 0 degree, and what I'm trying to do here is represent a basis of 0 degree a horizontal polarization and a vertical polarization, 90 degrees. And so I can say 0 degrees or around 90 degrees, which would be around here. And that is one way to represent our photon data. Another way to represent our photon data is to polarize it at a negative 45 degree angle or a 45 degree angle. And so with these 2 pairs, you can encode a 0 and a 1 appropriately. And so using this, Alice, who's our sender, will encode each of her photons in a certain way. Each photon will be either in the 0 90 degree format or the negative 45 degree format. And then that photon will go to Bob, who will in theory have another one of these, and he will decide how he wants to assume the photon was encoded, either in the 0 90 degree format or the negative 45 degree format. And then that'll go into the beam splitter here. Now if Bob guesses correctly, then the photon will either go here or here 100% of the time, or in a true quantum setup, it'll either go here and here. But from an outside all-knowing observer, they'll know which one is the correct one, that whatever resistor gets triggered is the one that is supposed to get triggered. Whereas if Bob reads it incorrectly, then there's a 50-50, because if the 2 basis vectors mismatch, it means that the photon's guaranteed to come at a diagonal polarization, meaning it's going to have to take a 50-50 chance on whether it wants to go here or here. Now, that'll happen for every single photon. When Bob decides to compare his basis with Alice in order to decide which photons were read correctly, they'd be able to match up for every single photon which polarization basis vectors were used. And whenever they match, Bob and Alice know that the data was correct, and they keep that data and form the key using that. And we can showcase here the idea behind whether or not you read a 1 or a 0. And here you can see that if the light is encoded at the 0 degrees, you can see our 0 resistor is being triggered. And then when the light is polarized at 90 degrees, it's over here. And you can see that while we don't have the second wave plate to represent a mismatch, say Bob receives somewhere in the middle, then you get around a 50-50 distribution, meaning neither the resistors pick up a value, and so there's your supposed mismatch. Here I'll show the fundamental behind how the BB84 algorithm allows for Alice and Bob to be able to detect Eve, who is our interceptor here. So there are basically 4 different cases that'll go on. When Eve matches Alice, basically when Alice sends out a photon and Eve correctly guesses which basis vectors for the polarization were used, then in both situations Eve is hidden, because when Bob and Alice agree, all 3 people agree on the photon polarization, and so Eve is correctly hidden. When Bob and Alice disagree, then the result was going to be thrown out anyways, so Eve doesn't get detected. When Eve gets it wrong from Alice, when Bob and Alice also got it wrong, then Eve is hidden for the same reason as before. But when Bob and Alice agree when Eve was wrong, that means there's a 50% chance that Eve selected the wrong polarization vector, meaning, or there's a 50% chance that the data gets received wrong by Bob, and Alice and Bob will see that and know that Eve must have been there. So in a real world setup, there would be a statistically significant amount of bits that are compared between Alice and Bob in order to essentially verify whether or not there was an interceptor.
Our future plans for this demo is to ideally have a full quantum setup. However, for the near future, the focus is to hopefully get an Eve component, the eavesdropper.
Yeah, so to add on to that, with our eavesdropper setup, we basically incorporate both Alice and Bob into one single modular component that could illustrate how Alice and Bob can detect Eve at any given time.